Hello and welcome everyone. My name is Michael Horn and today I'm working on homework 3, part B. And in this equation we will have two things on our itinerary. First, we're going to derive the closed loop transfer function for three identical gravity drain tanks in series with a proportional only controller manipulating that flow into the first tank and to control the liquid on the third tank. And then secondly, we'll be using the final value theorem. I will be referring to it as FET, and we will show that with the proportional controller and the head of the third tank will always exhibit an offset relative to that set point. That reduces the controller gain, which we will note as KC. So as you can see on my screen here, we have our three tanks in series. We have all of our flows labeled. We have Qn, H1, Q1, H2, Q2, and H3. And then we also have our tanks listed with their equations inside, k over tau s plus 1 and 1 over k, and that is then repeated in this tank. So these are the three identical, and then these two go along with each other. So we can begin writing our equation for this system. Now to get this equation, we will be solving for this H3 value. So we can imagine a big arrow there, and we will say that H3 is equal to all of these equations in these tanks combined. So we're gonna, instead of writing this out and wasting time, we'll take this, we will copy that, we will say that, and then we will also be taking this, because it'll be multiplied by 1 by k. And so essentially you're gonna go through tower by tower, and what you will arrive to is an equation as such. Oops. All right, not working. Whatever. And then finally, you will be multiplying everything by that big Q in value. So we now need to construct this loop that the question is asking for. And so as the arrow goes in, we will have the value of the height set point. This will be going into our controller. And then from our controller, we will have the flow of our error, in which our error will be going into another square. This square will have our KC value, which is our controller gain. And then from here we will have Q in. You know what? We're gonna adjust this for so we can make things fit a little bit better. Bring you over. And then move you over. Perfect. And now, like I said, this Qn is going into another square labeled as GP. And now from GP, you're going to have your exit stream of H3, but you will also have this loop go down, down and back. And here we will have another square labeled as GM. And then this flow will go all the way back into the controller. And this value does not have anything, we'll just put a plus or minus there, and from here we are able to make another equation. There are actually two things that I forgot in this loop. We need to indicate that this is equal to a 1. And then here we need to say, okay, well, what is GP equal to? We'll write it in here. GP is equal to our K value over tau s plus 1. And that all to the third power. Now we'll be incorporating two things. One called the forward loop, which I will write here in red. Or not loop, just the forward, sorry, because it will not be looping. And then we also have our open loop. I will demonstrate these forward, sorry. Now, The forward loop will be moving in a linear line, and this will be the numerator of our equation. So we will draw a big red line here. So this is, I will write forward. Now we have our open loop. This open loop will do similar, but not the exact same. Just imagine, I'm trying to think where I can draw this. We're actually going to grab you and move this down just to give some space. And as I mentioned, this will be going all the way around, so it stops there. It does not continue out to H3. And it will go down and around. So it creates sort of this loop look. So now we will be looking to get equations for our E value and our H3 value. And to do this, we will say E is going to be equal to our height set point minus H3. And then our H3 variable will be equal to GP. Again, we're getting these from the loops times KC. And then this will all be multiplied by the difference between our height set point and H3. So when we distribute this out, we get to the equation H3 equals GPKC. And now this HSP is going to be rewritten as H3SP because it is specifically held hand in hand with this H3 value. And then we will be subtracting GPKC times H3. So now here we want to get H3 all on one side. So I'll walk us through this. We have H3 plus GPKCH3 equals GPKCH3SP. Now here we take this H3 out to get 1 plus GPKC. And then the final section of this, we will divide both sides by this 1 plus GP value, and you get H3 equals GPKCH3SP all over 1 plus GPKC. So now, as you can see, we have this equation right here with our red box. And again, we'll list this as transfer function, TF. And now if you go back to what we did in part A, I'll scroll up here, you can see a very similar equation where we have a value multiplied by a numerator denominator polynomial multiplied by our q. Same thing here. So what we're going to do here actually is draw another function in which we have H3 going in. We have this transfer value in the side, GPKC divided by 1 plus GPKC. And then we have our flow out, which is H3SP. So now we are going to get our equation for the open loop. And to do this, we are going to write first what our E value is. And now we will be looking from here through these two boxes down, and we will be stopping here. So to get this equation, you have E is equal to our H3 times GM minus HSP. Then we have H3 is equal to GP GC times our error value. Now plugging that error value in, we have H3 is equal to GPGC times H3 GM minus H3SP. And so now what we are trying to get is our closed loop transfer function. And so from here, we will do similar algebra as we did above, so I'll kind of skip that step. And you arrive at H3 is equal to GCGP over 1 plus GC, GP, GM. And we're actually going to rewrite this as GOW for OL for open loop. And so we arrive right here. And we'll say that this is our closed, because it stopped, closed loop transfer function. So next we'll be incorporating our final value theorem, and this was specified in the problem statement. So let's write out the equation for this. And now this will be listed as the let's use black font. The limit as s approaches 0 will be equal to our s times y value, which is also equal to the limit as time approaches infinity, which is that same y value. And so now from here, we are going to use the equation that we actually used above. And so we will say h is going to be equal to GCGP over 1 plus KCGP. And this will be multiplied all by HSP. And then we can actually rewrite this as A over S. And so now, using the method that we used in part A of this problem with deviation variables, we're able to rewrite this limit into the limit of SH as S approaches 0 into the limit as H approaches 0 is equal to our KCGP times alpha over 1 plus KCGP. Now the final step in this limit is to break down this even more, and you arrive at an equation of KCKIA over 1 plus KCK. So now I will write our final equation that we've been looking for, and that is H is equal to KCKA over 1 plus KCKA. Okay, sorry. And now, so to recap what we did, we used this final value theorem, and from the equations above in the forward and open loop that we derived from this 3-tank system, you get to this equation. But you could be thinking, okay, well, what exactly does this mean? Well, you think, okay, what if I were to set this KC value to, let's say, 10 versus 1,000 versus 1,000,000, whatever. You would realize, okay, as I am increasing this controller gain, you will be getting closer to a value of 1. And so what this means is that our relative offset will be decreasing. So in summary, when you increase your KC value larger and larger, you'll be closer to a value of 1, you'll be approaching it. Therefore, my lighting is terrible. Therefore, your offset will be smaller and smaller and smaller. Thank you for watching.